Welcome to the next video in a course in real analysis. This is lesson 4 on bounds. In this video, we're going to present the definition of bounds, minimum, maximum, infimum, and supremum, see some examples and non-examples, and some exercises. I think in this, the exercises are going to be some theorems that we'll use later on. Now, I want to motivate why we are studying the topic of bounds, and it's because, well, in analysis, the use of bounds is an important proof technique. A bound will essentially allow you to take some kind of complicated object and replace it with a simple number, right? It may be hard to see exactly what I mean by this before I've even told you what a bound is and what the particular applications will be, but hopefully it makes a certain amount of sense if you know that, if some kind of mathematical object maybe occupies some region in space and we put some kind of a bound on it telling you approximately where it's located in space. But this bound maybe has a, like a radius m or something like that. And if you can prove something about the bounds, then perhaps you can use that information to say something about the object that is bounded by it. That's the rough idea. I'll show you a specific application in just a minute. But, not every bound works out, right? Sometimes this method of sort of trying to simplify a complex object by, sort of, in a sense, approximating it by a single real number is too simple and doesn't lead anywhere, but so often it actually is productive that it's just a very important thing to study. So let's look at this particular example, which is the sequence of numbers, the first number being cosine of 1, right? And keep in mind that this is like measured in, let's say, radians. So the cosine of 1 is some kind of complicated decimal if you think of it in terms of its decimal expansion, but it's divided by 1. And then the next number is cosine 2, also cosine 2, very complicated, but cosine 2 divided by 2, cosine 3 divided by 3, cosine 4 divided by 4, and you get the pattern. In general, if we wanted to describe this as a function of each natural number n, starting at 0, let's say, starting at 1, then we would say that this is cosine n over n. And this is a quite complicated thing because the cosine complicates anything that we would try to say about this sequence in general. And in particular, we're often very interested in limiting behavior. That should be a familiar interest from, maybe like a previous course in calculus. But so we're interested in the limit of this sequence. And so if we try to approach it directly, that's going to be quite difficult. But we can use a bound on the value of the cosine function. And so we know that the value of cosine n, no matter what n is, and I mean, this is not just for the natural numbers, but for any possible choice of number, cosine n is always less than or equal to 1. And so that's a nice, useful bound. And so using this bound, we know, right, like not only do we get a bound on just cosine n, but we can use that bound to give us a bound on cosine n over n, right? So at the very least, it would be negative 1 over n, right, with cosine set to the least value that it could possibly take, which would be negative 1. Or on the other end, we could set cosine n to the largest value it could possibly have, which is 1. And then we know that cosine n over n is bounded below by negative 1 over n, bounded above by 1 over n. And then, now here I'm going to give an argument that relies on the squeeze theorem. Possibly you've seen that in a previous calculus class, but the idea is intuitive. We will make this intuitive idea more rigorous much later on, many videos from now. But I think if I just rely on the intuition that you've probably already gotten from calculus, then this is still a motivating example. So since the left-hand bound goes to 0, right, this part right here goes to 0. as n goes to infinity. And then this part goes to 0 as n goes to infinity. And so since this is in between, right, the limit of this must be in between 0 and 0, so it must also, right, the only number like that is 0. So this number in between also goes to 0. And so notice that like what was a complicated object, cosine n over n, we didn't have to think about its complicated behavior. We didn't have to know too much about cosine n because we could put a bound on it, and then because our interests were in the limiting behavior, and the limiting behavior of the bounds was enough to tell us what the limiting behavior of the object itself does. So that is the sort of classic real analysis technique for a wide variety of theorems, is to set up some kind of bounding behavior and then look at the limit as the bounds do this or do that. So that is a core technique of analysis, and that's why in this video we're going to talk about bounds in a general context, and then we'll apply them to real numbers when we get around to that. Now, we just looked at an example of a bound on a sequence, which you can also think of as like a bound on a function. And there are many other things that we will talk about being bounded, but the most basic concept of a bound is the bound or a bound on a set. So let's start there. Let's suppose that we have some poset that is ordered by preseq, and then let's suppose that we have some non-empty subset of x, which we're going to call y, and then we also have this element alpha in x. If alpha, this by the way should be a preseq. It's still pretty clear what I was saying here, but just if I'm calling it preseq, I should use preseq consistently throughout. But in any case, so if alpha preseqs everything in y, we say that alpha is a lower bound for y. Obviously, there's a dual. If everything preseqs alpha, everything in y preseqs alpha, then we say that alpha is an upper bound for the set y. Now, just for some further vocabulary, if a set has some lower bound, then we say it is bounded below. If a set has some upper bound, we say it is bounded above. And if it has both, we say that it is simply bounded. Now, let's look at some examples. Let's consider the natural numbers ordered by the usual less than or equal to on the natural numbers. And let's consider the subset y equal to this, what is this? I guess this is basically the set of odd numbers starting at 5. Let's list all of the numbers that are lower bounds for this choice of y. Certainly 1 is, and by the way, I think I'm using the book's convention. If I remember correctly, the book does not use 0 as a natural number, so I'm gonna not use 0 as a natural number. If I, correct me if I'm wrong about that. I think I recall that the book does not use 0 as a natural number. So if we work on that with that assumption, then 1 would be the sort of the least lower bound, then 2, 3, 4, and notice technically 5 is also a lower bound on this set y, right? Even though 5 is in the set, it is true that for every element of this set, 5 preseqs or is less than or equal to every element in the set. And since this set goes off to infinity, right, it has infinitely many elements going, there is no upper bound, right? For any number that you might offer as an upper bound on the set, we'll always find one larger, so it has no upper bound. So next, let's consider a more sort of, so to speak, abstract example, where we again used a system of sets, namely the power set of this set ABC, and we will order these subsets, this system of subsets, by the set inclusion relation. And let's consider in particular that this is our example subset Y, right? That is a subset of the power set. Now this, let's talk about its upper bounds. Certainly this, the set of AB, is an upper bound because for every possible member that you could choose from Y, that would be like an instance, that would be an instance of Z, right? So this would be like in what I said for the definition, this would be like an element Z in Y. And then it is a subset of the set AB, and that is true when you select this for Z, but it's also true when you select the set AB for Z. So that makes the set AB an upper bound on the set Y. Another upper bound on the set Y would be the entire set ABC. And then through similar considerations the other way around, the set of just A is a lower bound on the set Y, and so is the empty set. And in fact, whenever you take any system of sets ordered by the set inclusion relation, the empty set will be a lower bound. And so, so long as you have a universal set, then that universal set, here the universal set would be like the set ABC, then that universal set will always be an upper bound. Now, for reasons that will become clearer later, we will have use for talking about the set of all lower bounds and the set of all upper bounds on any given set. So let's give a definition and some notation for that. So again, we take any poset X ordered by preseq, we take I guess I should say a non-empty subset of X, and then to talk about the set of all lower bounds of Y, we write this notation LB sub Y. So that's the set of all Z in X such that Z is a lower bound of Y. Likewise, we have this upper bound notation. The set of all upper bounds is UB sub Y. So returning to the same example as before, where we take the natural numbers ordered by less than or equal to with the subset of the odd numbers starting at 5, the set of all lower bounds is the set 1, 2, 3, 4, 5. The set of all upper bounds is the empty set. Now, although there is a whole set of lower bounds, like for example, in this example, right, there is a set of lower bounds, but clearly just one of the lower bounds is the best lower bound. And it's the number 5, of course, because 5 is the lower bound that is nearest to the set. In fact, it's so near that it's actually in the set. Like, in a sense, the distance is 0. Right? The distance between the number 5 and the set is 0 because it's in the set, in a sense, right? I'll define the notion of distance to a set maybe in another video, but just take that. This is a little moment where I'm trying to motivate the notion of a best lower bound and also a best upper bound. So for now, we're going to be just a little bit informal and just sort of appealing to your intuitions. I think that in some sense the best lower bound is the one that is in some sense nearest to the set, and in this particular case that's the number 5. And so whenever you have something that is a lower bound but also in the set, that is a fairly distinct best lower bound. Conversely, for the upper bound, right, if an upper bound is in the set, it is clearly the best of the choices of bounds. And so we sort of canonize that with the definition of minimum and maximum, right? That's just what the minimum is. The least element in a set is always a lower bound of the set and also a member of the set. So that's the minimum, and that is, in formal terms, some element, right? Some value in your poset, some alpha in the poset, which is both in the subset Y and also a lower bound of the set Y. So that's what it means to be a minimum of the set. And then there is obviously a dual definition for the maximum. As a matter of notation, when alpha is the minimum of the set Y, we write alpha equals min Y. When alpha is a maximum of, or the maximum of the set Y, then we write alpha equals max Y. And let's look at some examples. And for variety, let's maybe don't do the natural numbers again. Let's look at the rational numbers, ordered by less than or equal to. But let's talk about the rational numbers. And let's look at this example set Y, which is the interval from 0 exclusive to 1 inclusive. So this set Y has no minimum, because, you can kind of tell that, like, well, we would want to talk about the minimum being like 0. In some sense, that's almost the minimum, but 0 is not in the set. And if you go any bit bigger than 0, well, then that's not going to be a lower bound, because if you take any positive number, there's going to be a number, in Y, because there's a number between, any positive number and 0, right? So if you pick, if you tried to take alpha equal to, I don't know, 1/1000 or something like that, right? A very small number, but bigger than 0, well, then there's always going to be some number in between 0 and this choice of alpha, and that's going to mean that alpha is not a lower bound on Y. So anyway, this is all just to explain that Y has no minimum, right? It's a demonstration that not all sets have a minimum. But it does have a maximum, and the maximum is 1. So we saw that it is possible for a set to have no minimum. Of course, it's also possible for a set to have no maximum. And yet, still, in some sense, there is a clearly best lower bound on this particular example, right? Even though 0 is not a minimum because it is not a member of the set, it is a lower bound, and it is the best lower bound, because still, in some sense, the distance between it and the set is 0. There's like no space in between that lower bound 0 and the set. So in some sense, the distance between them is 0, meaning that 0 is still the best lower bound for this example set. But we couldn't call it the minimum. So what do? Well, then we just sort of expand our notion of what a best bound is. So somewhat informally, a bound is best when it is, okay, a bound, but also nearer to the set than every other bound. So that's kind of what we mean when we talk about a best possible bound. Again, saying a lot of this semi-informally, and we will make this more formal later. And in fact, here is exactly how we make this more formal. So we will, again, consider a poset X ordered by preseq. We'll consider a non-empty, I should say non-empty, can't read that, non-empty set Y, subset of X. And we do need to talk about it having a lower bound, which is to say the set of lower bounds on this non-empty subset Y. The set of lower bounds is not the empty set. So this Y has some lower bound. The best lower bound, if it exists, is the maximum on the set of lower bounds. And this we call the infimum of Y. So the, some mistake here. So that should be inf, don't know how that happened, but okay. So the max on the set of lower bounds is called the inf. Try to sort of appreciate that intuitively. So for instance, if you're thinking about this example, which I'm sure I write this example later on, but let's just see it right now. If you think about this, and imagine this interval taking place on the number line, so that like 0 is right here, 1 is right here, and and we know that all of these numbers here, all the numbers to the left, up to and including 0, all of these numbers are lower bounds on the set. And this is, so basically this yellow is a representation of the set LBY, right? It's the set of all lower bounds on the number 0. And the best lower bound is the maximum of that set, right? It's the one that is closest to the set Y. And we could play this game all over again to the right of the set, right? All of these numbers up to and including the number 1, this is UBY. And the best possible choice of upper bound is this minimum. This set does have a minimum. That minimum is the number 1. So that actually happens to be both the maximum of the set and the supremum of the set. And in fact, because that's the minimum of the set of upper bounds. We will actually prove in one of the exercises at the end of this video that when a maximum exists, it is also the supremum, right? So all maxima are suprema, but not the other way around, right? So sometimes, like, here you can see right, this is on the other side, right? This is the dual of that. So we'll talk about infima, but here we see that it is possible to have an infimum that is not a minimum, right? So all minima are infima, but not all infima are minima. But let's briefly take a moment to appreciate how important this is for the concept of the real numbers. And so let's consider the rational numbers ordered by the less than or equal to relation. And let's consider, just for example, this set 1 to infinity, 1 exclusive. This set has neither a minimum nor a maximum, but it does have an infimum, which is the number 1, and it has no supremum. Now, that's just for, that's not terribly interesting. But now consider the same poset, right? The same rational numbers ordered by less than or equal to, but this time consider the set 0 to square root 2 exclusive on both ends. Now, you may not like talking about 0 to square root 2 when we're talking about the rational numbers, because after all, square root 2 is itself not a rational number. And so you might think, well, writing an interval like this, right, using a real number when we're in the context of a rational number might seem invalid. It's not entirely invalid, but if you have any qualms about that, then we can reframe it, right? We can recharacterize it by instead just talking about the set of all rational numbers which have a square bigger than 0. Well, actually, that is just all numbers other than 0. And also are smaller than, right, their square is smaller than 2. So in effect, this is the set if you try to draw it on the number line, right, and we mark 0 here, then this set would include all the numbers, again, right, put negative root 2 here, even though that's not a rational number in the real numbers. Let's just imagine that's where that is. And let's put root 2 over here. And then this set, if we imagine it, it would be all the rational points in between, but not including 0, right? 0 would be excluded. In any case, so long story short, that's roughly what this set is. And this set does not have a supremum. And that's a big deal because, the whole idea of a supremum was to say, well, sometimes we can't have a maximum. But, still there's a best upper bound intuitively. So let's expand our notion of an upper bound so that we capture what is clearly still this best upper bound, right? So that would be like in the example of, I don't know, say 0 to 1, this number 1 would be, not a maximum, but it is still a supremum because it's clearly still the best upper bound. But this is a big deal because it doesn't even have that, right? It doesn't even have a supremum. So what do we do about that, right? I mean, like we expanded from maximum to supremum in our concept of a best upper bound in order to catch more cases that we obviously desired, but it's not helping us here. And this is moreover, this is a set that is bounded above, right? The number, I think, the number 2 is going to be like out here, and the number 3 is somewhere out here, something. Well, I can't even draw it. Why can't I draw it? Okay, well, anyway, so there's some issue with the drawing application there, but in any case, right? The point is this set does have upper bounds, and some of the upper bounds are better than others. You can even form this sequence of upper bounds that gets closer and closer to the set, but that sequence is not going to have a minimum, right? Which is what you need for the supremum, is you need the minimum. It doesn't have a minimum because, in some sense, if it were to have a minimum, it would be that square root 2, but that's not a rational number. So the point here is that when dealing with the rational numbers, you can actually have sets that are bounded above, but do not even have this expanded notion of a best upper bound. There are infinitely many upper bounds, and any one that you pick is not the best. So what do we do about that? Well, we'll see more about this in future videos, but this is exactly why the real numbers were invented effectively, right? It is precisely this deficiency of the rational numbers that, and, you might say, oh, but didn't we have the notion of square root 2 as like a real number that's not a rational number in ancient times before we ever sort of came up with like these ideas of analysis and so on? Well, yes, but you could even there kind of construe that as thinking that like the fundamental issue is these gaps that we need filled for simplicity in some sense. But anyway, so this deficiency about there being some sets that have upper bounds but no least upper bound, no supremum, that is exactly what the real numbers will not suffer from. We will have an axiom stating precisely that, right? It will be an axiom of the real numbers that every set which is bounded, every non-empty set, again, I should say non-empty, but every non-empty set bounded above will have a supremum that is, in fact, the thing that distinguishes the rational numbers from the real numbers. All the things that we have said so far about fields, about orderings, about compatibility. Well, have I talked about, I think I have not talked about compatibility. That's in the next video. But in any case, all of these things that we will say about like the structure of numbers, basically, is just as true for the rational numbers as it is for the real numbers, except for this. This is the thing that distinguishes the rational numbers from the real numbers, is that for the real numbers, every set which is bounded above will, by an axiom, have a supremum. Okay, let's get into some exercises. So for a first exercise, notice that in the definition of minimum and maximum, we say that a set has, or that some number is the minimum, right? Using the definite article, the word the, indicating that there is just one. And intuitively, that is true. But it is not, right, from just the concept, right, that it would be an element of the set and also a lower bound of the set. That definition does not trivially imply that there is only one such element. So although we speak about it using our intuition that there should only be one such element, it does deserve a proof, and that's what this exercise asks you to do. So take any poset which has a minimum and show that there cannot be a second distinct minimum. Probably by this point, it's clear how that proof should be structured. Essentially what you're going to say is let alpha be the minimum of this subset Y, and let beta be another minimum of the subset Y, and then show that alpha must equal beta. That's the outline structure of the proof. But yeah, there you go. Also, when you're done doing that, show that if a set has a minimum, then that minimum is also the infimum of the set. Actually, it occurs to me I should also have assigned, because it is thematically similar and just as useful, to know that the infimum is unique. And in fact, actually, I can already see how a nice proof of that would go. So yes, also prove that and try, right? So here, let me give you some guidance on that. So also prove that if a set has an infimum, then the infimum is unique. And as a strong hint for a very nice and short proof, use what you've already shown for, well, maybe minimum, but really maxima, right? So everything that we say here, which is true for a minimum, should also be true for a maximum, and also everything that we say here for an infimum should also apply just as well to a supremum. And so you can get a really nice proof, a really short and concise proof of this extra tacked on exercise by appealing to what you showed here, although not for the minimum, but instead for the maximum. But in any case, okay, so there's your first exercise. Okay, next, show that if you have any poset with a singleton subset, so Y will be the set of just A, where A is some element of X, show that in this case, Y has a minimum and a maximum. It's a very simple idea and result, and a very simple proof, but it's just an exercise to help you to warm up to using these concepts. For a slightly more interesting and challenging exercise, suppose, and this time specifically, that you have a totally ordered set, X ordered by preseq, let Y be some non-empty finite set. Show that Y must also have a minimum and a maximum. Hint, use induction on the size of Y. I give you a little bit of guidance here. I won't talk you through it, but you can read the guidance here if you want any more of a hint about how to approach this problem. And finally, for the last exercise, suppose that you have a poset X ordered by preseq. Suppose that Y is a non-empty set subset with a minimum, which we will call alpha, and suppose that beta is some element such that beta is less than alpha. So effectively what I'm saying is take something which is less than the minimum, show that this element cannot possibly be in Y. This should be a fairly simple and short proof. And finally, I'd like to end this video with an invitation to ask questions. If you found anything in this video confusing, please feel free to write as specific a question as you can in the comments below. If I can address it in the comments, then I will. If it's a substantial question, then I might make a whole video and include it in the playlist.